Hi, I'm THAM LI JING. My research topic is differential cryptanalysis of the lightweight block cipher boron. This is the contents. We will start with the introduction followed by the background to introduce the area that this research will be focused on, the research methodology, implementations, and results before we conclude. Firstly, I would like to discuss the background of this research project. Cryptology is a general term that includes cryptography and cryptanalysis. Cryptography, specifically encryption, converts the plaintext into ciphertext with the usage of secret key. Cryptanalysis decrypts the ciphertext into plaintext without the usage of secret key, while block cipher is an encryption method that encrypts a block of plaintext into a block of ciphertext. Differential cryptanalysis discovers differential truths, which is the propagation of input to output difference to be used for attacks. This is the symbol form of differential truth, which delta x represent the input difference and delta y represent the output difference. A differential is a cluster of differential truths that start or end with the same input or output difference that can improve the efficiency of the attack. In this research project, the differential cryptanalysis on boron cipher will be carried out. The motivation of this research is to contribute towards the cryptographic community and data security by producing new cryptanalysis results for boron cipher. One of the research problems is boron cipher has a lack of cryptanalysis results. Since 2017 until now, there is only one existing research work that related to cryptanalysis of boron, other than the security analysis that done by the designers. In addition, prior cryptanalysis of boron cipher does not consider the concept of differentials. The implementation of differentials can lead to more efficient attacks. The objective of this research are to produce new differential cryptanalysis results for boron cipher and to optimize the differential search to efficiently cluster differential truths for boron. The scope of research is focus on differential cryptanalysis of block cipher boron. Besides, set solver is applied to search for differential truths, and the differential search algorithm is modified to make it adapt to boron structure. Next is the background and related work. In our research work, we were looking at boron, which has 25 rounds, lower memory requirements, and faster speed than present. The authors claim that it is better than some of the well-known ciphers, while having the same level of security. If the claims are true, boron can be a good replacement for these ciphers. But boron still lacks cryptanalysis results. The first cryptanalysis work about boron is the introduction of boron cipher proposed by Bansod in 2017. The result of Bansod's work is that there will be a minimum of 48 active S boxes with total differential probability of 2 power of negative 96, which still need to be verified by other cryptanalysis works. That's why there's a need for more cryptanalysis works. There's another cryptanalysis work with the title Cryptanalysis of Boron Cipher using SMT solver, which performed by Liang and Wang in 2019. The result of this prior cryptanalysis work are able to construct a differential truth for 8 rounds with a probability of 2 power of negative 62 and use it in a key recovery attack on 9 rounds of boron. The limitation of this prior cryptanalysis work is that they do not consider the concept of differentials. The next section is discussed about differential cryptanalysis. As stated in introduction, differential cryptanalysis seeks to discover the differential truth to be used for attacks. Differential truth is the path from one input difference to one output difference, while differential is multiple differential truths that begin from same input difference and end at the same output difference. By clustering the trails that start from the same delta x to the same delta y, the overall differential probability will be improved or increased. Thus, key recovery attacks that use these differentials will be more efficient and may allow cryptanalysts to attack more rounds of the cipher. For our work, we are using branch and bound for clustering because it can cluster efficiently, but it cannot guarantee to find the best single trails. So set solver is used because it can find the best single trail efficiently. But the computational effort for clustering scales exponentially to block size. This is the flowchart of detailed research methodology. First, literature review is conducted to study existing block cipher and differential cryptanalysis. After carrying out these literature reviews, block cipher boron has been chosen as the target cipher for this research, and the branch and bound meet-in-the-middle search algorithm has been chosen as the technique that will be modified and applied in this research. Next, simplified forward-backward permutation is implemented for testing the meet-in-the-middle concept. The forward and backward permutation is required to speed up the clustering, which will be described later on. The results obtained are compared with the previous cryptanalysis work to verify the correctness of the forward-backward permutation algorithm. Then, the forward and backward differential tables are calculated and generated. The differential search for clustering is modified to be adapted to boron structure. By using the differential trail obtained, the cluster of differential is searched and the differential probability is obtained. By using the differential probability of the cluster that obtained from the differential search, a new key recovery attack complexity can be calculated. The first section of implementation is permutation mapping. The diagram shows the simplified structure of boron after performed permutation mapping. Although boron seems to have a complicated permutation layer, but in this research we find out that it can be simplified to a series of XOR operations. The table shown is the differential distribution table, which records the number of occurrences for the corresponding pair of input difference and output difference. The first step of generating the differential distribution table is assigning the values to input x, followed by applying the value of x box of boron cipher as output y. The next step is discover the difference pairs of x box, then followed by record and tabularize the number of occurrences for the difference pair. Same step will be carried out to generate the reverse differential distribution table by just reversing the S-box operation. In the implementation, set solver is used to find the best single trail, the starting point for the clustering. The set solver produces the result by checking the satisfiability of constraint. Generic branch and bound search is used to check the correctness of the modified algorithm before implement the forward and backward version for meet-in-the-middle clustering. The generic branch and bound algorithm is modified from Matsuri's algorithm. The modifications that have been done are the implementation of permutation, XOR operations, and differential tables to make the algorithm adapt to boron structure. Since Matsuri's algorithm is structure dependent, thus the modifications are necessary. The branch and bound meet-in-the-middle search algorithm is modified and applied to search for a cluster of differential trails and obtain the differential probability. In this algorithm, meet-in-the-middle approach is implemented. The cipher is divided into half. Then the number of paths for each search direction becomes smaller. Thus, by reducing the number of rounds in the forward and backward search, a smaller number of branches can traverse effectively. By searching fewer rounds, the computational time can exponentially reduce. In order to make this algorithm adapt to boron structure, the permutation layer is modified. Next, we will talk about results and evaluation. The first section is the verification of program correctness. The generic branch and bound search is modified and applied to search for best differential trails for up to 3 rounds of BORON. The result obtained are then compared with the result from previous BORON cryptanalysis work. In 3 rounds BORON, the differential trail and differential trail probability obtained is same as the previous work. Hence, the correctness of the modified generic branch and bound search algorithm is verified. This table shows the differential probability obtained from the proposed cluster search and the differential trail probability from BORON previous cryptanalysis work. The branch and bound meet-in-the-middle search takes the best differential path and optimal differential trail of probability that obtained from generic search as input, then produce the differential probability as one of the outputs. By clustering the path that begins and ends with the same input and output difference, the differential probability can become greater. For example, in 8 rounds, the differential trail probability is 2 power of negative 62, but the differential probability has been improved to 2 power of negative 58.156 after clustering taken. This table shows the probability of each path included in a differential cluster for a particular number of rounds. The sum of the probability of each match pair path is equal to the overall differential probability. For 6 and 8 rounds, the path X and path Y have n number of forward paths, which implies that clustering has occurred even in the forward search itself. For example, in 6 rounds, the path X already consists of 2 forward paths inside, and path Y consists of another 2 paths. This table shows the differential cluster result that obtained from the branch and bound meet-in-the-middle search. Take 8 rounds as example. For 3 rounds of forward path, with the error of 1 exponent negative 6, and 5 rounds of backward with the error of 1 exponent negative 4, we will have 159 million forward paths and 412 million backward paths. From all of these paths, 111 met in the middle to produce the final probability of 2 power of negative 58.156. The next table shows the execution time of differential clusters. For example, in 7 rounds, for 3 rounds of forward and 4 rounds of backward, the execution time is 267 seconds. While for 4 rounds of forwards and 3 rounds of backwards, the execution time is 867 seconds. Different round combinations are tried in differential search to achieve better cluster result. For example, in round 8, the differential probability is improved slightly from 2 power of negative 62 to 2 power of negative 58.156. When the number of backward rounds is greater than the number of forward rounds, the differential search will be more effective. When the error values used is lower, the differential search will become slower, but larger cluster can be obtained, and vice versa. BORON takes fewer rounds to achieve close to 2 power of negative 64 differential probability as compared to present, L-block and twine, which means that BORON can achieve a similar security level with fewer encryption rounds. Besides, BORON also takes fewer paths to achieve improvement in the differential probability. Thus, there exists multiple differential paths with the same large probability starting from the same input difference to the same output difference. This implies that BORON's differential cryptanalysis result can be improved if a longer clustering search is performed with looser bounds. In key recovery attack, the 8th round with a probability of 2 power of negative 58.156 is taken as the distinguisher. Then, a key recovery attack on 9 round BORON is performed by adding one more round at the end of the 8-round differential distinguisher. This is the input of the input difference and the output difference of the distinguisher. Then 2 power of 58.156 plaintext pairs with the difference is chosen. The result obtained are as below. Time complexity is 2 power of 56, memory complexity is 2 power of 24, and data complexity is 2 power of 59. In previous boron cryptanalysis work, the data complexity is 2 power of 63 for a key recovery attack towards 9-round boron. Therefore, a new key recovery complexity result for boron is produced in this research. The contributions of this research project include: discover a better probability for 8 rounds of boron, present the differential cluster result of boron for 4 rounds to 8 rounds, and produce new key recovery complexity result for boron. The future works for this research topic are as below. The clustering for 9 rounds is currently running, and due to the high differential probability we obtain, it may be possible for us to add 2 rounds to the tail to attack 10 rounds of boron. Thank you. That's all for my presentation.